Okay, so something called parametric equations. It seems a little confusing at first, but what you're doing is you're taking y equals f of x and splitting it into two equations. And you're adding a third variable called t, or it could be another letter like theta. Um, this is typically used often in physics, because in physics, if you think about it, if you're dealing with two-dimensional motion, is anyone taking physics right now, by the way? Yeah. Oh, wow. Okay. um, but we have sophomores in here, right? Not many? Okay, but you're not doing physics, obviously. Yeah, okay. Anyway, wow, a lot of people doing physics. Okay. Um, yeah, so anyway, when you're dealing with like physical motion, right? Two-dimensional motion, you want to see how things are moving horizontally and vertically. So sometimes we want to break apart some sort of equation, like say, for example, you're looking at like y equals x. I don't know. I'm just trying to think of a good example. I'm kind of lost on examples right now. But bottom line is like, what if you want to get the horizontal motion in terms of time and the vertical motion in terms of time? So you want something that kind of relates that. That's one reason why we have parametric equations. There's other purposes for it too, but we won't get into that right now. But let me just show you an example so you see how it works. And then we'll move forward to the next page. So example 12, and we'll totally revisit this much later in the semester. Probably not until like late October, early November is when we'll revisit it. And we'll really kind of get deep with it. But for now, I'm just kind of scratching the surface. So you have two equations, x equals t squared minus 4 and y equals 1/2 t. So you're asked to sketch a curve when t is between -2 and 3 by making a chart and plotting the points. And as y a function of x, we'll answer that in just a little bit. So here's what you're going to do. You're going to make a 3-column table. You have a t column and x. I should make that bigger. Actually, let me do it on this side. I'm gonna need more space. Let's do it on the right side here. So they say let t be between -2 and 3. So I'm gonna do -2, -1, 0, 1, 2, and 3. And let me make this table a little more organized. Kind of these like crosshatches, if you want to call them that. So let's look at x. If I plug a -2 into the x equation, what's x going to equal? And if I plug -1, what's x going to equal? And if I plug in 0, what do I get? And if I plug in 1, I get -3. So it's kind of like a parabola, right? And 5. Cool. Okay. Now, let's do the same thing for y. I get -1. Half. Net with -1/2. 0. Remember, plugging t in, not x, plugging t in. So be careful. 1/2. 1. And 3/2. But this is really what you're plotting. That's really what we're plotting. So 0, -1, -3, -1/2, -4, comma 0, -3, comma 1/2. So it's totally not a function because it's going to fail the vertical line test. 0, 1, and 5, comma. So what am I making? What does it look like to you guys? Sideways parabola, totally right. Thanks, Sebastian. Totally 100%. Yeah, 100%. Looks like a sideways parabola. So the answer is no, because fails the vertical line test. Okay. The answer is no. It totally fails vertical line test. So what if I wanted to get x in terms of y or y in terms of x? So limiting the parameter, what that means is you want to remove t. Any ideas how I can remove t? How would I substitute? Is it good? Anyone have an idea? David, go ahead. Yeah.
I don't know. You could put,
David, right?
yeah.
Yeah, here you go. I just want to try to get names right.
You could put 1/2 t squared minus 4.
Or you could get t by itself in the second equation. That could work. Just avoid fractions. So let's say t equals 2y, right? So then x equals 2y squared minus 4. which kind of makes sense because that would lead us to a sideways parabola. So that's called eliminating the parameter. So how does the graph of this equation differ? Well, if I were to graph this, it actually would be more complete, right? It wouldn't stop just like this. What additional information could be provided so that the graph of this equation will match the one in part A? You need to restrict the domain. Oh, sorry, the range. That's what I meant to say. Right, right. So additional information. Yeah, you want to restrict the range. Exactly right. So let me show you how you can do this with the graphing calculator in case you guys are curious. And again, why do we have this? There are times in physics or other applications where you actually want to like get X and Y in terms of different variables. Like time would be one thing, X, Y, or like horizontal, vertical movements, stuff like that. So in the graphic calculator, here's how it's done. Here we go. Okay. You're a USC fan? All right. Okay. I'm a Stanford fan, but we don't play each other anymore now, so the rivalry's dead. But Stanford and USC had quite the rivalry back in the day. Yeah. They were fun games. Stanford sucks now, football. All right. Anyway, so in case you guys are curious, and guys, I am recording this, so you guys will have a chance to watch this again, and we'll revisit this later on. So if you go to mode, if you switch to parametric, hit y equals. Notice how this changes. So again, what I did is I went to mode, I went to the fourth line and switched from function to parametric mode, then hit y equals, and you can see how that changes. So now I could just type in my equations, and t is where x would usually be. So t squared minus 4, enter, 0.5t, enter. And then if I go to window, I'm going to restrict my t from -2 to 3. Did Mr. Band spend time with you guys doing graphic calculator stuff? Kind of, not really. Okay. Now, the t-step's interesting. The t-step means how frequently the points will be plotted from -2 to 3. The smaller this is, the more accurate and smooth the graph will be. So notice my t-step was 1, right? Because I just did it by intervals of 1. So if I switch that to a 1, keep x and y all the same. See, it looks kind of rough, right? But let's say I make that more smooth, like 0.1, or more fine. Or let's say I did 0.01. It's going to take even a 0.01. See what's happening there. I think I did break it, actually.
Oh, no, it's just going really slowly.
Yeah. So what is it doing? It's literally plotting 0.001, 0.002, or sorry, between -2 and 3. So it's doing -2, then -1.999, negative 1.998, negative 1.997, negative 1.996. So it's taking a sweet little time. So we got some time. Yeah, go ahead. So go to mode. I did fast. I'm sorry. Go to mode. Let's switch to fourth line to parametric. So hit y equals. Have that stuff. Oh, go to mode. It should be where you see functions. Switch to parametric. Okay. Okay, it's still taking a sweet little time. I should have known better not to do 0.001. So you go to y equals. Okay. That was not smart what I did. So let's switch to the 0.01. That's a little more appropriate, I think. That one was way too long. It wasn't really necessary. Let's see, what if I did this? What if I made my t-step 2? See, it's not quite that complete, right? So it's just interesting to play with a little bit, like how accurate you want it. So, or how smooth. Anyway, we're done with that. That's just something I just want to kind of touch on. Let's spend more time on this stuff here, analyzing functions. I care more about this. Let me resize this. Okay, here we go. So let's talk about increasing, decreasing, and constant portions of a graph. Increasing is when y increases as x increases. So the graph is rising, as you would imagine. Decreasing, y is decreasing as x increases. So the graph is falling. Here, y doesn't change. As x increases. So the graph is flat. Another way you can think about too, using kind of a calculus kind of explanation. What if I drew a line that's tangent to the graph? You guys know what excuse me. You guys know what tangent lines mean? Okay, let's go back to zero for that.
Wait. Tangent is like basically 1 point.
Not trig. From a plane geometry perspective. So you guys remember what that means? It raises the graph, right? It touches just once. That's what a tangent line means. When it just raises. So if I drew a tangent line to this curve right here on the left side, what's the slope of that red line? Positive or negative? Positive. When that's positive, the graph is increasing. Or the graph stays rising. Now granted, as I draw different lines that are tangent to the curve, the slopes will change, but still it's positive until we get to over here. All of a sudden, they're flat. Still positive here, but what happens if I drew a tangent line on the far right side? Right. That's how you can tell whether the graph is increasing or decreasing. So I'm actually giving you a little bit of calculus right now, believe it or not. This is kind of beginning of calculus. And we will talk about this in the spring. But that's another way you can kind of tell whether the graph is increasing or decreasing, is if you drew a line that just grazes the graph, the slope of that line will tell you if it's positive slope, it's increasing, negative slope is decreasing, and of course it's horizontal, it's flat or constant. So in this case, where is my graph increasing? It's totally gonna be increasing from negative infinity up to -2.
3 to 5.
And 3 to 5, exactly. We'll make it inclusive. Yeah, that's a really great question to bring up, David, because there was much debate as to whether you should include that or not include it, because it does kind of stop increasing at 5. Sometimes on the AP or the on the AP exam, the College Board, they sometimes just say just give us an open interval just to avoid that debate. But whether you include or don't include, I'm not going to hold that against you. I say just to be on the safe side, include it. Now, where's it falling from what to what? 5 to infinity, totally 100%. And where's it flat?
2 to 3.
Yeah, that's all. That's all there is to it. Yep. Now, before I move on to the next topic, I want to kind of just simmer on this graph a little bit. Some questions. That makes sense? I got that. So think like a roller coaster, right? If you board the roller coaster on the far left side, and x is always increasing. So as we move from left to right, are you going up or down? Are you're increasing elevation, right? Like you're anticipating, and all of a sudden it's flat. Then you're rising again, and then you drop. You drop at x equals 5. Now you're falling, right? So you can feel like that. That can work. That's one way to think about it too. But yeah, now I know what I want to say. There are transition points, right? When you switch from increase to decrease, or you switch from decrease to increase, right? If you switch from increase to decrease, that's a peak. The peak we call a max, which makes sense. But when you hit a low point, you kind of like hit a trough, you want to think like that. If you hit a low point, that's a min, right? When you go from decrease to increase, that's a min. So that's what we're going to talk about in the next part B. Relative extrema. And I'll explain why we use the word relative in just a moment. It's a little confusing at first, but I think the explanation I just gave in terms of where you see that transition from increase to decrease or decrease to increase, That should help. So extrema, that's a plural of extreme. We don't say extremes. That's terrible grammar. Extrema is a plural for extreme. First, the highs and lows in a graph of a function. There are two types, absolute and relative. Now, absolute means the highest possible point. Highest or lowest possible. So I'll give you some examples in just a little bit. I don't want to make this too messy right now. Relative just means within the neighborhood, right? Can I use a real estate as a good example? Because real estate's kind of interesting. So let's consider Silicon Valley. Where do you think we'd have the absolute absolute max home prices? What community do you think we'd have the craziest, most expensive houses? Probably here. Where else do you think, maybe?
So
Woodside for sure. Yeah, Woodside's crazy expensive, right? Yeah, maybe Hillsborough, perhaps. But let's talk about maybe Redwood City, though. Are there like $15 million homes in Redwood City? Probably not, right? Maybe $4 or $5 million homes. But within that neighborhood, if you're like maybe you're like Mount Carmel, Edgewood, that area, in that neighborhood, sure, maybe you could say that's like a relative max, right? Relative like, within that region, right? I know I'm not sure that makes too much sense, but relative means like within the neighborhood. Absolute means the highest possible. So relative to the points around it, that's what it means. So hopefully that makes sense why I use the word relative. Sometimes you use the word local, like locally, if you live in Redwood City, like okay, what's the highest home price or lowest home price, stuff like that. So the definition of relative and relative min, relative max. If you have a confined interval, x1 to x2, and let's say f of a is the local min, then what this means is that as long as your x values between x1 and x2, then f of a is less than or equal to f of x. That means that f of a is the lowest y value for any x in that region. So let me give you a graph that might help. Say this is x1. Say this is x2. That's x2. And I don't know, I'm totally making up some stuff here. And say C is right here. A, sorry, my bad. Some textbooks use C. My apologies. So let's say A is right there. So f of A is less than any y value in that region locally. If this is your local, so like, think about like an x1, x2, right? Like, let's say this is the city boundaries, like, like right where Chavez Meat Market is. I think that's the boundary between Redwood City and Menlo Park. Right where the Trader Joe's is, that's kind of border between Redwood City and San Carlos on El Camino. So within that region, this would be like the lowest home price if you want to think about that, right? So it's just within that interval. That's called, but there could be a lot of crazy stuff happening afterwards. Like, I don't know. Maybe afterwards the graph does like some weird stuff like this. No idea. But locally, that's the lowest point for now. And then vice versa, if you want local max, then f of a would be greater than or equal to f of x. So the way that could look graphically would be kind of like this here. Locally, that'd be the highest point in that interval. So that's what's meant by relative extrema. And going back to that previous example, if I drew tangent lines, right? Notice that the tangent line was negative before I got to A, and then switched to positive after A. You see that transition, right? From falling to rising. That tells you have a relative min. Or, let's try this again. If I do this here, if I do tangent lines here, try that again. Yeah, see how that's going from rising to dropping, positive to negative slope, right? So yeah, that could happen. And so that would be a relative max. And by the way, absolute extrema also count as relative max and relative mins. It's just absolute gets a very special designation. It's kind of like it's all squares or rectangles, right? Right, but not all rectangles are squares. Squares are very special, quadrilaterals, kind of the same thing. So here's what we're going to do. We're going to evaluate a certain graph and determine their mins and maxes. And let's do this in the graphic calculator because you do need to be comfortable with it. I don't imagine, and again, you guys are not doing AP calculus for another year or so. But I don't imagine the College Board is ever going to switch to Desmos for AP exams. Maybe they might. Who knows? Maybe. But for now, the TI-84 calculus is kind of the standard for AP calculus classes. So let's go to the calculator. Let's punch this in. By the way, we got to switch our mode back to function. So go back to mode, switch back to function, go back to y equals, punch it in, x raised to the third power, minus 3x squared, minus x plus 1. And I'm going to graph in the standard window. It's just more appropriate, Cool. We're okay? If anyone doesn't get that, let me know. I'll come by and help you out. We're good? No problems? Cool. Okay. I'm just going to try to do a rough sketch here. Y-intercept's 1 for sure. A-okay here? All's good? Sweet. Okay, so in here. So A, we took care of. All's good. My viewing window, I went to Zoom standard. I like that window. It seems to work for me. But how do you find where it's increasing and decreasing? How are we going to do that? What do you guys think we should do in the calculator? You guys know? Yeah, so how do you find the highs and low points in the calculator? What button do you guys press? You guys know?
Second trace.
Good. Second trace. Okay. Ms. Brand teach that to you guys? Yes, no? Or some of you guys just know? Ms. York taught you. Oh, okay. All right. All right. So you go to so let's find a high point. That's clearly P. Now let me ask this question, guys. Is that the highest possible point for the graph?
No.
No, because what's the highest possible point? Do I know? The sky's the limit. I have no idea. It's a polynomial. If the polynomial has an odd degree, there's no way we're ever going to have an absolute max. It just goes up forever. If it has an even degree, depending on whether the length coefficient is positive or negative, there could be peaks or low points, depending on whether it's opening up or down for deflection. But yeah, sky's the limit, but that's a relative, right? So that's a relative max. And then is that an absolute min or relative min? Relative, yeah. We don't have an absolute min. I don't know. There's no floor. There's no base thing. It just goes down forever, right? So let's find it. Let's find a max first. So when you do the max, it's going to ask you 3 questions. It's going to ask for left bound, right bound, and a guess. What you do is you move the cursor a little bit to the left of where you feel the max is going to be. Hit enter. And notice it stores, there's a little arrow that pops up. It stored that value in that equation. So it knows, okay, that's the left side of the beat. After right bound, do the same thing. Just move it a little bit to the right where the peak is. I mean, you can move it more right if you want. So now the calculator knows I'm only going to investigate x values between these two x values that are stored here for left and right. I'm only going to check stuff in between. And the calculator is going to do all these little calculations, split seconds, until it whittles its way to the middle and realizes, oh, which one's the highest y value? So it's going to realize, okay, a little bit to the right of this left endpoint, okay, the y values are getting higher. A little bit to the left of this right endpoint, y values are getting higher. Then it's just going to be somewhere in the middle and realize, oh, I've reached the peak now. So as for a guess, just hit enter. It's just going to do the calculations. The guess is kind of arbitrary. Just hit enter. And there you go. That's your peak.
Sorry, so much. Where should I like put left down, right down?
To the left of the peak and the right of the peak.
Oh, to the left of it?
Mm-hmm. That's why it's left bound. And I do the same thing for min. Rinse and repeat.
How can I put it to the left of it if it just keeps on going?
No, you deliberately move the cursor to the left of where you feel the type is. So, oh, hold on. Oh, you're not there yet. You can't see it. You got to get closer. Now you can see it. Enter. Enter.
So you do it just left and right in the middle?
Exactly. Right. Right. Okay. Let's keep moving here, guys. For the min, enter. I don't know what that is. Okay, 2.15. Hold on. Negative 5.079. Yep, there we go. So where is it increasing? So from negative infinity to negative 0.015, sorry, negative 0.155. And again, from 2 point. So that's increasing. My bad. That's confusing. My apologies. Let me erase that arrow. Okay, where are we decreasing between those two numbers, right? Correct. Correct, right. Mm-hmm. You got it. And then when you state the maximum, here's how I want you guys to state it. We're gonna get really technical with our terminology. Just get in the habit of doing, I mean, again, you guys are not doing AP Calculus for a while, but I want to get you guys in the habit of writing it. So we're gonna say relative maximum of 1.079 at x equals negative 0.155 relative minimum of negative 5.079 at x equals 2.155. The reason why I prefer you write it this way is that when you're asked to find what is the maximum value, you're being told, give me the output that's the lowest possible value. Oh, sorry, relative maximum, give me the output that's the highest value within a certain interval. And give me the lowest y value. So the relative minimum is actually a y coordinate. Not actually y coordinate. But you guys know where it happens. It happens at x equals this and x equals that. In terms of context, so one application of this would be like find the area of like trying to maximize the area when you do some parameters. Great example would be like if you're doing like a bunch of like fence posting and like you got like 30 feet of fencing, you want to maximize the area. You know, that's the output. So you usually want to kind of state the output and what dimensions it happens at. That's just the habit of what you want to write kind of this way. Does that make sense? Okay. And the calculator kind of did the dirty work for us. We just punch it in and just extracted the values from the calculator. By the way, Desmos does this better, as you can imagine. just mouse over and you're there. You're good, right? So cool. Okay, in example 3. And I do want to do page 13 as well. And what time do we get out today? We're good. 125. We're good. Okay. Here's a word problem. Okay, good. I like this. I like context here. During a 24-hour period, the temperature of a certain city can be approximated by the following model, where T represents time of day, T equals 0, which refers to 6 a.m. So we're doing for a 24-hour time frame until 6 a.m. the next day. Graph the function in a calculator, indicate the viewing window, use it to approximate the 2 decibels of the maximum temperature during this 24-hour period. Okay. So you can go from 0 to 24 clearly, right? And when I plug in 0, I know I get 34. So gosh, it's 34 degrees Fahrenheit. That's cold. Probably winter. And of course, that corresponds to 6 a.m. I'll do 12 here. That corresponds to 6 p.m. And that's going to be 6 a.m. the next day. Okay. Well, let's punch in the calculator. See what happens. So let's see, we got 0.02. I should clear this. 0.026 x raised to its third power minus 1.03 x, cool, plus 10.2 x, cool, plus 34. I should change the window though. What's a good window here, guys? Well, yeah, we'll go 0 to 24 for x. And I'll make this intervals of 4. It's up to you. I don't really care. The y, do we care about negative temperatures? Not really. I'll probably do like 0 to like maybe 80. I don't know. And then make that 20. Okay, that wasn't good. That was terrible. Did I punch it in wrong?
Oh, you didn't take 1.03
You are so right. See, I made a mistake, guys. I'm human. Thank you. Yeah, I knew that was weird because it had to come back down. So here's the thing. Okay, this is good. I'm glad this happened. Okay, so I'm human. I make mistakes, right? But I know my math. I've got, my college degrees. I've been here 20 years. I have confidence in myself. I expected that graph to come back down because given that the degree is 3, right? I'm expecting something to do this, right? So I know the graph is funny, right? Because I know my concept. So I just made an error. So point being is that when those mistakes happen to you on a test, don't feel you don't know. You know. You guys know what's up. You're just human. You make mistakes. So to have more, just have faith in your abilities. Don't worry if things don't work out right. I knew something was funny. So I knew instantly to check my inputs. I knew I probably punched something wrong. Okay, now let's try it again. Okay, now I feel better about this, right? I feel much better about this. Okay, good. So it's going to look kind of like this, right? Which kind of makes sense because it does get hotter, in the middle of the day. That's 6 a.m. So probably in the afternoon sometime before evening time, then it starts going down in the evening, then it'll start heating up again when it gets closer to morning. So that's my peak. And let's find it. Very simple. Now you guys know. Second trace, option 4. Move that cursor a little bit to the left of where you feel the peak's going to hit. And now it's falling again. Hit enter. A little bit to the right of wherever you feel that peak's going to be. Hit enter. Sweet. So it happens at 6.6. And temperature is 63.93 degrees, or roughly 64 degrees Fahrenheit. 6.6 is about like 12:30-ish, 12:40-ish in the afternoon. So kind of makes sense, right? Given the context. So we're cool. Yeah, so that's just using the calculator to analyze it. Pretty simple stuff. Last thing I want to talk about is greatest integer function. And then we'll stop there after that. All right. Have you guys talked about this before? Greatest integer function? Is this new to you guys? Yeah, you have? Okay. Well, it's really simple. It's like a rounding function.
Oh,
You didn't? Okay. No, don't worry if you haven't. Okay. It's like a rounding function. You pick the greatest integer less than or equal to x. So for example, but it rounds down. It actually rounds down, just so you know. Doesn't round up, it rounds down. So if you have 3.5, what's the greatest integer less than 3.5? 3, right. Yeah, exactly. There it is. That's all.
Not that hard.
If you happen to have an integer, then it's just the input, right? So the greatest integer less than 2.6 is 2, 1, -5, -3, and 0. That's all it is. It's not that hard. Let's look at the graph. And by the way, in the calculator, I think it's under math. Yeah, it's option 5. If you hit math and num, 3.5. Yeah. So if you go to math, then num, option 5, it's right there. If I put -4.5, we'll say -5. Yep. So actually, that's good I found that because we're going to graph this. Example 6. Okay. I'm going to make a little table first. What's the greatest integer less than 0.1, guys? How less than 0.9? How about 1? Because less than or equal to, right? Still 1, then 2. So here's what's going to happen when I graph it. I'll go to y equals, hit math, num, option 5, x. And let me go to the standard window. Look at that. So it's called a step function. It's like a step with a interface, right? It's a little confusing to see at first. Let me resize the window. Let's go from 0 to 10. And 0 to 10 for x and y. So it's going to be like this.
Finish is fun. You guys have Jenga for your thoughts? Yes. Never mind. I extended my previous statement.
Okay. So think about it, guys. By the time you get to 1, it jumps. You get to 2, it jumps. You get 3, it jumps. So it has to jump to the next level. So now you're no longer less than that number, right? So like, for example, 2 is greater than or less than or equal to 2 is 2 and so forth. It's not continuous, by the way. There's a bunch of gaps everywhere. But your domain's still all real numbers. The domain is still all real numbers.
How do you get that on your graph perspective?
Yeah, sorry, I did it kind of fast. You go to math, and then num, and then option 5. That's how you get there. We'll go to y equals first. You gotta go y equals first. And then that's how you call it up. Okay, the range is, guys, quiet please. The range is interesting. How would you write the range for that? All, not quite. Not all whole numbers, all integers, yes. It's hard to write that in interval notation, so I just write all integers. The x-intercept's obviously 0. And y-intercept's obviously 0 as well. So yeah, that's all there is to it. That's called the greatest integer function. No, because that oh, you are right. You are right. Sorry. Yes, you're correct. I was wrong. The x-intercepts. My apologies. You are 100% correct. The x-intercept is going to be, yeah, you're right. The x-intercepts from 0 to 1 at the interval, because there are infinite x-intercepts.
confined between 0 and 1, 0 inclusive, 1 not inclusive. Correct. I didn't, yeah, you're 100% correct. There's like a gazillion x-intercepts, like 0.001, 0.999999999, like 0.87432, like whatever, right? There's a whole bunch.
But it's confined between 0 and 1. 0 inclusive, 1 not inclusive. My apologies. Mhm. Yeah, go. All right, I think I'm done with the notes. Perfect timing. Great time to do the homework quiz. This is exactly what I want. 10 minutes left. Perfect. Here we go. Here's the homework quiz. 10 minutes.
Oh, yeah.
Homework quiz. Here we go.
Oh, but we didn't know within the,
So the law of the way 24.
no, no. Why'd you take my calculator?
You're kidding, right? Literally right there.
I thought it was over here.
No, you do.
Okay, everyone's got one? Cool. I'll do it too. I bet I need to make an answer. And no need to simplify. Don't worry about that. Or rationalize. I don't care. You don't have to show terribly much work